We just learned what a polar rectangle is, and we did an example of integrating over a polar rectangular region. So just to tackle a visual with that, I have the constant values of r, or the radius, marked out by blue arcs, and constant values of theta marked by these green rays originating from the polar origin. This white shaded area is the region that we're looking at integrating over, and we can see that it exists between two values of constant radius. So we have the radius that we're calling A at the inner portion, and then the radius that we're calling B along the outer portion. And it's also squeezed between two constant values of theta. So the lower theta, the one closer to the polar axis, we'll call that alpha. And the theta that is further away from the polar origin, we'll call that beta. And so in a polar rectangular region, we have constant bounds for the radius and for the theta. And so integration over this region D, underneath a function f that takes in variables r and theta, we would have that area increment r dr d theta, because that comes from our dA, the area increment. And then to set up our bounds, we would just put the constant values for r on the r integral and the constant values for theta on the theta integral. And if these are both constants, r and theta, then it doesn't matter which order you integrate with respect to. You could do theta first if you'd like. You can do r first if you like. Doesn't matter. But now that we know how to do these rectangular regions, let's take a look at general regions. Just like we did in rectangular coordinates, we started off with a very simple region stuck between constants, and then we described a more general region. And in rectangular coordinates, we said there were two types, type 1 and type 2. I called them vertical and horizontal, and we said depending on the type of region you're looking at, the order of integration is predetermined. Something very similar will happen here in polar coordinates. So again, we're looking at this region D shaded in white, and we can see that the radius is not stuck between two constants along this region. If I were to draw some lines to see the radius, I would see I'm stuck between two wiggles. I'm not stuck between constant values of radius. So the inner boundary line, I'll call that h1, a function of theta. So as theta changes, the radius value is changing along this curve. And then that outer boundary that defines the outer radius, I'll call that a function h2, which the radius is changing as theta is changing. So my radius is squeezed between two functions rather than between two constants for this very general looking region. Theta, however, is still going to be between two constants. And that's basically one of the best parts about integrating over a polar region, is that you can guarantee that theta will be squeezed between two constants. Even if the region just comes to a little point, we can say that once that radius spans over the region, there's going to be one little point that exits at a constant value of theta. So even though we're looking at a really general region, notice that this is not a well-defined function. This is a very squiggly region. We can set this up using constant bounds for theta and function bounds for r. And just like with rectangular coordinates, whenever one of your variables is bound between constants, you have to integrate that variable first. So when we are integrating general regions, where the radius is not squeezed between two constants, the order of integration has to be dr d theta. And that's because r is depending on a function, whereas theta is depending on a constant. So when it comes to defining the bounds for integration on these general regions, I have some short little list to help guide you through it. to find the R limits of integration, we're going to start at the origin, and we're going to grow a ray. So I'm going to grow a ray that goes through the region. And if it's not obvious with one ray, you can grow a couple of them. And each of the rays that I'm growing, the point I'm trying to get is that I can see where the ray enters the region. We enter along this h1 function. So I know that's my lower limit for R. And then I can see that each one of these rays is exiting along this boundary, which is defined by this function h2 of theta. And so to find the R limits of integration, we grow this ray through the region, take note of where the ray enters the region, where the ray exits the region, and those will be your lower and upper bounds for R. Now let's talk about how to find the theta limits. The theta limits say to imagine that you have a ray on the polar axis, and you allow that ray to sweep across the region. So I'm drawing multiple of them rather than trying to animate with one of them. And this is going to be useful because we'll be able to see at what angle the ray touches the region first, and then the rest of these rays are inside of my region, and then there's going to be one more ray over here that exits my region. So the theta limits are going to be from alpha to beta. So with these two tips, we'll be able to find the lower and upper bounds for each of the variables R and theta. Let's practice finding some of these limits for integration. So for this problem, we're looking at a region inside a cardioid, which is described by the equation R equals 1 plus cosine theta, and outside the circle R equals 1. The first thing we need to do is draw this picture. Now, we could make a table of values and sketch this ourselves, or we can pop into any of our favorite graphing programs to generate a picture. So the cardioid is here in turquoise, and the circle with radius 1 is here in fuchsia. And we're trying to find the region that's inside the cardioid, but outside of the circle. Well, inside of the cardioid is this full space. But some of that is inside of the circle, and we don't want the inner part of the circle. We want outside of the circle. So our region is what I'm shading in here with white. And remember, to find our limits of integration, we're going to start with our R bounds. So starting at the polar origin, I'm going to draw rays or grow rays that come through my region. And I'll keep adding more until it's obvious to me where all of the rays are entering and exiting the region. So I can see that each of the rays I've drawn started to go into the region once we passed the pink line. So our lower bound comes from that circle R equals 1. The upper bound, that's where the ray exits our region. I can see each one of the rays I've drawn has exited along the cardioid. So the 1 plus cosine theta will be the upper bound for R. Next, we can look at each of the rays that we've drawn to see how they sweep across the region. Now, originally I said, let's imagine that we have a ray that starts on the polar axis, and then we rotate it until it passes over our region. But if our polar axis is in the middle of our region, we might need to kind of wind it back. And so if I drew a ray down here at slightly less than negative pi over 2, I'd see that I'm going to enter the region as soon as I hit negative pi over 2. And then I can let those rays rotate until I come up to the top over here. And if I were to draw a ray at that edge, I would exit the region at positive pi over 2. So my theta bounds would be from negative pi over 2 up to positive pi over 2. Now it is important to describe theta as negative pi over 2 up to positive pi over 2, rather than trying to use the coterminal angle 3 pi over 2. Although those are equal angles, 3 pi over 2 would not fit the inequality that we've set up for theta. So it's important that this inequality is consistent, which is why we're using negative pi over 2 instead. Let's try another one. Practicing to set up the bounds for polar coordinates. So we're looking at the area enclosed by the equation r squared equals 4 cosine 2 theta. Again, the first thing we need to do is create a visual for us to see the region. So we have that visual here on the screen, and the area that we are going to calculate is inside of this little bow tie. So we need to define the bounds for r that fit within this picture. Now, the goal of this problem is to find area. So if we think back to our double integrals to calculate area, remember that we kind of fudge the double integral. Instead of integrating underneath a function, we integrate underneath the constant 1. And that allows us to get the same scalar representation for area, although it's technically a volume. So we're going to do the same thing, but in polar coordinates. So we'll have our double integral over our polar region. We integrate underneath the function 1, and for polar, dA gets replaced with r dr d theta. And so now we just need to find the bounds of integration for r and theta. Now, because we're integrating underneath a constant function 1, and we have symmetry within the region R, we can do some shortcuts here. So instead of integrating over this entire 0 to 2 pi, I'm going to say, let's look at one section and then we'll replicate it. So how about from theta equals 0 up to whatever theta corresponds to this ray? What if we just looked at this area? Can you tell that that's 1/4 of the total area inside of this curve? So if that's the case, then we can just calculate this area, multiply it by 4, and find the total area. So let's do that. In order to do this, though, we do need to figure out what that larger value of theta would be along this top ray. So to find that, we kind of need to look at the equation r squared equals 4 cosine theta. And notice that when theta was 0, our function was here. And then as theta increased, the value of r decreased. And it came all the way down to 0. So we would like to know what would have to happen to this equation to make r equal to 0. Well, the 4 is not the thing that's going to cause r to go to 0. It's going to be the theta, and it's cosine of 2 theta. So we would need to think of what angle should we plug in to cosine 2 theta to make r equal to 0. Well, we know that cosine of pi over 2 is equal to 0. So what we need to do is make pi over 2 equal to 2 theta. And then solve for theta. So we'll divide by 2, divide by 2. We get theta equals pi over 4. So that upper theta that we need for our bounds is going to be pi over 4. We also need to figure out the radius range. So we draw our radius starting at the polar origin, and we grow a couple of rays through the region, and we can tell that each one of these rays is exiting along the curve defined by r squared equals 4 cosine 2 theta. Each one of the rays, by the way, started in the region because that polar origin is part of the interior of that region. So for our r bounds, we know r equals 0, we're already in the region, and then we need to think about the largest value of r we can use. Well, again, it's defined by the equation r squared equals 4 cosine 2 theta. But that's r squared, and we're talking about r, so we need to make sure to take the square root of both sides of that equation so that we can see the largest value of r will be the square root of 4 cosine 2 theta. Now we can set that up so that we can integrate. So our double integral over the polar region, under the constant 1, our values are going to go from 0 up to the square root of 4 cosine 2 theta, and then theta will go from 0 to pi over 4. But remember, that's only 1/4 of our area, so we're going to multiply that integral by 4 to get the total area. And I will leave that for you to integrate on your own.